So anyway, I thought I'd talk about something fun, which is some old work, but I've begun to think about it again since. And anyway, so this is kind of a neat thing. So this is the world's worst drawing of something you will recognize shortly. So anyone recognize what I'm very poorly attempting to draw? All right, this, yeah, I figured this might then make it easier if I did that. Does that help any? It's still that bad? Anyway, it's supposed to be a drawing of Europe. See that? If topologically it's correct, I think. Right, so the key, it's Germany and France, Belgium, Netherlands, Denmark, Spain, Portugal, Italy, Luxembourg. I didn't include Monaco. Oh, let's include Monaco. Monaco is just bubble in France. So anyway, so the problem I'm going to talk to you about is, where this is useful, is the chromatic polynomial, which started out measuring the number of ways of coloring a map. So this is a function of q. So pi of q with q colors such that adjacent countries are colored differently. As an American, I just spelled color incorrectly 3 times in the same sentence. But anyway, and so, I mean, the point is, so if we color Germany blue, you know, then you can, since we have colored chalk here, we can then color Belgium purple. If I did this right, we should have, do I have enough colors? And then I can color, actually, France purple again. Netherlands does not border on France. Belgium, we can do that. And then Luxembourg, we have to have another color, which we don't have here. Oh, wait, we got yellow. So then Netherlands would have to be that. And so there's a, you all know, there's this famous 4-color theorem that says any planar map can be colored this way. But before that was proved, and by what most people consider a sort of proof that's not terribly elegant, you know, there's this beautiful reduction of all possible planar maps to a finite number, but the finite number is really big, so you have to then use the computer. It's pretty tedious and ugly, so people, we're still maybe looking for another way of doing it. Various famous mathematicians have weighed in on this. But and before this was proved, and maybe still now, people like me, thinking about a slightly more general object. And so we can rephrase the statement of the number of ways of coloring in this object, the chromatic polynomial. And the way it's usually written, it depends on some graph. Let's call it, for reason, let me follow my conventions here. So let's call that, yeah. So I'm gonna call it a graph T because eventually I'm gonna restrict to the case where there are triangular relations. Of course, this is defined for anything. And the way we do it is so I draw this map of countries, and the map of countries, so these are the borders. But then if we, let's pick another color here. If we draw the dual graph to this, so these are the vertices of the dual graph. And then we draw an edge between them if the two countries are adjacent. I get Monaco in there, and so forth. So this gives us a graph. So let's do something now after my very bad drawing. Let's do something a little simpler. So if we have, for example, the graph there, that's my boundaries between countries, I'll then draw the graph T to be that. So this is T, and this is T hat, the dual graph. And so then, so in this particular case, we can pi of T would be equal to Q. So say we color that with Q colors. Well, that one has to be different, so times Q minus 1. And then this one has to be different than both of those, so then it's Q minus 2. And you notice it's a polynomial in Q, and it's easy to prove. It's unique. And so thus, we can define this for all Q. So not just integers. So Q, complex numbers. Right, although everything, all the Q's I'll be talking about are real. All right, and so sorry. So for this one. And the way you can prove this, that it's unique and all that, is an important relation. It's what's called the contraction deletion relation. And what it says is, if I take the graph, so take any graph, I've got some edge on the graph, and then it goes off other ones, so some edge. Well, the chromatic polynomial of this thing will be equal to the chromatic polynomial of the thing where I contract the edge, so the same thing there, minus the chromatic polynomial of the same thing with the edge deleted. So that's why it's called contraction deletion. There you contract the vertex, you contract the edge, join the two vertices, and then all that. And from the country point of view, it's kind of obvious. So again, this is one country, that's another country. These are all other ones. But what it's saying is either, so in the case, we can just get rid of the edge. But then the catch is now if this and this country, so this country and that country and this thing could be colored the same. And so I have to subtract off the one where they're colored the same, otherwise I overcount. So that's all the contraction deletion is. And so it's easy to see any planar graph, I'll come back at the very end to mumble about non-planar graphs, that this thing is defined uniquely. And if, in fact, via the contraction deletion relation, we just need actually a few other things here. We just need the fact that if we now have, when we have an isolated point, so I'm using green for this, so we have an isolated point, then that gets just a weight Q. There's some other things, I mean, these aren't all independent, but these are useful to know. So if we have something like this, again, this one goes off like that, well then this, for example, implies that this will be Q minus 1 times that. That's just saying, again, that can be any of Q colors, so if that one has Q minus 1 choices. One more, if we have something like that, that equals 0. Because a country can't border itself, because you can't color the same country, two different things. All right, so that's some neat stuff. And so some of you may know, was a lot of cool old stuff about zeros in this thing. So then, so the four color theorem is just a statement It's just the statement that chi of t for greater than 0 for any planar graph. So that's neat. Okay, so what people then noticed again, long time ago, there's some famous results by Baraha, Kahani, and Weiss, which I'm not going to talk about, but definitely inspired this sort of stuff. So one of the neat things is this chromatic polynomial has very special properties. So people started analyzing the zeros. In fact, a long time ago, I went to a conference here at Newton, solely devoted to studying zeros of the chromatic polynomial. If you look in the complex plane, they have all these remarkable properties. I'm not going to say anything about Q complex today. It's all going to be Q real, but there's still some very curious things. So for example, at special values of Q, there's interesting zero structure. And so, again, that's a big story, but let me just show you one thing. Well, so if we take Q equals 2, and so again, let me draw it in the dual picture because we're going to move over to this dual picture where I'm drawing the boundaries between the countries. So this one would look like this. So if you have something like this, well, this has to be 0. So if you have a triangle ever, so maybe there's other stuff going on out here, but if you ever have a triangle, it's got to be 0. And the reason is sort of obvious. Well, because I color that with Q colors, that has to be Q minus 1. That's because they have to be different, but then this one has to be different from both of them. If you have only 2 colors, that's 0. And that does not obviously follow from the contraction dilution relation. I mean, at the end of the day, of course, if you try and compute the chromatic polynomial of any graph, you'll end up reducing it. But it doesn't instantly happen. You'd have to go through the whole thing to see it. And so anyway, so this is almost trivial. But the point is Tutte, who I think is one of the gods of combinatorics, noticed some other funny stuff long time ago. This one is in his book. I'll only tell you 2 funny identities for the chromatic polynomial. I'm writing so far down. So 2 funny identities for the chromatic polynomial of specific values. In fact, well, I'm going to focus on, for the most part, one specific value, and I'll give quickly some generalizations. So what Tutte showed is the remarkable thing. So let's now, I'm going to go I'm going to always draw, it's easier for me to draw the boundaries of the countries. So not the original, not the green ones, so the clear ones. So the boundaries of the countries. All right, and so that's why for that's equals 0, Q equals 2. To remind you what Tutte showed, just purely by mucking about as far as I can tell, just when you're a genius, you can muck about in a productive fashion. And he found the following identity. So if you have boundaries of countries, it looks like this is just a parentheses. Those are the boundaries of the countries. If you draw things like that, so you have four countries here. We have countries A, B, C, D, D, etc. So that would be A, C would have to be equal to D. A equals B, D. So you count all the ways of doing this embedded in some bigger graph. So embed, this is true for embedding. T-hat, dual of the other one. So he showed that this identity is true cubed equals 5 plus 1, and 5 plus 1 is the golden mean. So it's pretty obscure. It's in, I think, only his book Graph Theory, as I knew it, as I have known it. I don't think he ever put it in. So this is a linear identity. So in other words, if the point is, so if you want to move this guy over to the other side, anytime I see this in a graph, I can replace it with this linear combination. Or another way of saying it is, let's say that one equals minus that one plus 1 over 5 cubed plus that. And so I can always replace it, and what it says is I'll get the same chromatic polynomial taking this linear combination than I would have if I had just stuck that in. That's curious, and it's only true when Q is the golden mean plus 1. So that's curious already. An even more bizarre one that's really useful for people who do such things, let me write it out carefully, is that is the following one. So back to my original. Is this nonlinear identity. So now it says take the chromatic polynomial of any planar triangulation. So now when I worked down before, everything was general. This identity only applies if this is a triangulation. That's in the original language where this is the graph of the, so the triangulation in T, so that means only trivalent vertices. T hat, which I'm calling G. So now it says you take the square of this chromatic polynomial, evaluated it, golden mean plus 1, times some factors, it's just the number of vertices in T, another constant, and you get the chromatic polynomial, another one. So that's 5 plus the square root of 5 over 2. And so this is even more bizarre because it's not linear. And so this is, if you ever write a program to generate chromatic polynomials, this is an amazing way of checking what you just did, right? Because any chromatic polynomial for any triangulation has to obey this. So to check your expressions, you just plug it into this. It has to satisfy this. Really remarkable and weird. So that's what I'm going to explain. So Tutte's proof of this long time ago in 1969, I think, was combinatorial. I mean, it's not that difficult, but at least I learned sort of nothing. There was no illumination coming from the proof. The result is amazing. And so what I'll tell you now today is I'll show how you can actually derive this. Well, actually both of these, and this one you'll see plays a role in this. In a really nice fashion when you talk about fusion categories. So again, people, at least many people here probably know what that is, and I'm not going to give the full-blown definition. I'll just give what I need for this proof. But let me just say a few words for those of you who do know. A fusion category comes up in topological quantum field theory, comes up in physics when you're talking about braiding and fusing of anyons. But what it does and why it's useful for what I want to do today is it tells you, gives you nice graphical rules, in nice ways of evaluating the fusion category. Gives you nice ways of evaluating graphs. And probably, again, most of you know this is Jones polynomial is an example of the kind of thing you can do. And the famous Jones polynomial, there's topological invariant. Well, the chromatic polynomial I just described is a topological invariant, right? It doesn't. That's why my European map was so poorly drawn, but it still would have given the correct answer. Because the chromatic polynomial is a topological invariant, and so you can embed those. And so for those of you who know what they are, I'm just going to say the words. It's related to what's called the O3 BMW algebra, and will be related to SU2 level K. Anyway, so for those of you who know something about that, that's what the particular fusion category is. But like I say, I'm going to skip all that. That's described in some old papers of ours, but the precise correspondence between the ideas of the fusion category. But the key concept I wanted to get through was these are topological. It's a nice way to get topological invariants. Okay, so let's now do that. So let me just define now what we'll call the chromatic algebra. Like I say, all this can be embedded, which I'll call CNQ. Q is our number. And what it is you just take all, so it's just spanned by trivalent graphs, all trivalent graphs that you can draw, and mod by certain relations. This is an ideal. And in fact, they're basically the relations. So the three relations are the following. Well, one, so I'm going to draw a disk. And when I draw a disk, and then I'll have this one will be empty, go to the disk. So this means what's outside the disk can be anything. And the relations apply to only what's going on the disk. So it's really important that everything is local. So I draw a disk there, and the relation that I mentioned before is, well, if I have a country that borders on only one other country, so this is like Monaco inside France, right? Well, then I can just get rid of that country, just forget Monaco, and then multiply the chromatic polynomial by Q minus 1. In this case, well, we're talking the chromatic algebra, then you multiply the graphs. So these are statements about the graphs. At the end of the day, they leave the chromatic polynomial invariant. So the point is this ideal modding out so that's one relation. Second relation is, again, we have a disk. And if I have only one line coming into the disk, and then I put a bubble on there, physicists like to call tadpoles, then that's 0. And again, from the chromatic polynomial, so this is the boundaries of the countries. Well, so this is saying that we have a country here, and then this has to be a different color, but of course I can move around that, and that would be the same color. So that doesn't work. That's 0. That's not the graph. That's just the number 0. And then the third one is the contraction deletion one, which you can draw in a bunch of ways, but I want to write it down for trivalent graphs, and it's going to, in terms of trivalent graphs, you can see it looks like this. And again, it says is this, if you have two countries here, well, this would mean they have to be different. This means they have to be the same, and then it would be the same. So those are the three relations. And then we define a trace on this. It gives us slightly differently normalized chromatic polynomial. So we define the trace of this. And so what we have, any collection inside this box, it's a bunch of legs sticking out. So again, that's my disk there. So a bunch of stuff going on in there. Okay, and then the trace just says is equal, so you keep that in there, and then everything just gets done around like that, and then we take the chromatic polynomial of that thing, and then there's a normalization factor, we divide it by q. And so this gives you a map from this chromatic algebra for complex numbers. So this is a valid, so you write down a graph, connect all of the things sticking out, and then take the chromatic polynomial that gives you a number. So we can do examples. I wrote one down here just to hopefully make it obvious. So everything I'm saying, well, I'll write it down here. So the trace, for example, of this, that's a graph. Also, I connect them up. So that goes to that. Goes to that. Goes to that. I want to take the chromatic polynomial of this. All right, well, so you get, I'm just going to do this by erasure now. I get a Q for coming from there. Then that thing is that theta graph I drew way back, and that gave us Q minus 1 times Q minus 2. And then we divide by Q, just for convenience, and so this was Q minus 1. Oh, and I lost, sorry. Oh, sorry, I made a big mistake. What was my mistake? Anyone paying close enough attention? When I removed this one there, I got the Q minus. That was a Q minus 1 coming from that, not a Q. And then I have the overall Q coming from the outside. So that's the one that cancels. So this is Q minus squared. All right. So that's an example of that. All right, so set this up so that everything I've said so far, well, except for quoting Tutte's results, has been just definitions. Those are the results I'm going to prove. And the way we prove this, differently from Tutte, like I say, basically just cleverly combinatorialized it out, but I'm not good at that, but I can draw pictures. So what I'm going to do is show that this chromatic algebra, so this is again just doing these, writing out planar graphs, modding out by those three things I listed there. We're going to show that you can map this on to, it's called the Temperley-Lieb category, Temperley-Lieb algebra. And I'll explain what that is if you don't know. Some of you, again, that's a common thing that comes up there again. And so to mention, well, this is like the BMW thing that I mentioned before, for those of you who know what that is. Okay, so what it is, so let me tell you what Temperley-Lieb is. And this is the thing that comes up in the Jones polynomial. Those of you who know how the Jones polynomial works. It says you take a 3D knot, you project it down into the plane, and then you replace overcrossings and undercrossings by a linear combination of avoiding graphs. And then, let's look at this quickly. So you take your grade, and then, so when you project the thing down, and you have some parameter q, that's the parameters the polynomial is in, and typically, some conventions, you'll replace that with that, so you get a graph of loops then, because we've resolved all the crossings. And so you get a sum over things like that, and then you evaluate it, which just means take some number d equals q inverse to the number of loops times all these things here. So to evaluate, so the Jones polynomial, you evaluate graph, which means turn it into a number, q plus q inverse times all those loops. And now, so that's the very world's quickest and poorest explanation of the Jones polynomial. For those of you who've seen that before, which I hope is all of you, that's where that comes from. Anyway, so so the key thing to take home is in the temporally Lieb algebra, the evaluation. So again, the evaluation takes a graph into a number. And here, it's much easier. This is just going to be loops. So the evaluation will just take some number d to be d to the number of loops. And so let me now systematize this a little bit. So again, so I'm drawing now strands. So let's show by example. So we have the temporally Lieb algebra on 3 strands. And it says now you can draw all non-crossing graphs. So this is much easier than what we were doing with the quadratic polynomial. So we have 3 lines coming in, 3 lines coming out, and so one way of connecting them would be like that. Another one would be like that, and another one would be like that. And so the algebra, so the generators of temporally algebra on 3 strands would be, well, this would call like the identity. This is called E1 typically, and then that's called E2. And likewise, and you can build up TLM by simply by words in the EJ, where just have more strands and all that, subject to the conditions. So E squared equals DEJ. So now this is for TL D M strands. We have EJ with J running from 1 to M minus 1. So that these subject to these constraints. So again, you draw all possible graphs, you mod out by this ideal. So E squared equals DE, and I'll draw a picture for it in a second. EJ plus 1 EJ, and let's get greater than 1. And so now Y, this is super cute, is the following. Well, so let's draw these pictures. So say back to TL3, I draw that picture, then I'm squaring it so that I connect it up to that picture. Then I have my rule that I mentioned, I take D the number of loops, I get that. So this algebra is the algebraic way of representing this evaluation of pictures. This one, well, I draw, let's draw up here where I wrote. I want to draw EJ plus 1, EJ. Well, I've got now that one, this coming along, got then this one, okay. So that's equal to that. And then the last one is just they commute when they're far apart. So this was dubbed at some point in the last 20 years de-isotopy, or maybe even longer than 20 years. So you can move lines around, and you can remove closed loops, and you get a factor D. So now, the way we prove this, we have to prove the golden identities. We need to prove something about this. I'll just tell you what the theorem is and give the proof in words. So, okay, so now what it says is, so now I have some graph over here. So again, it's triangulations in the original chromatic polynomial picture, so that means it's trivalent vertices when I drew my countries. And that's true of Europe, right? There's no place where in Europe 4 countries meet at a point, is there? In the US, there's 4 states that meet at a point, but I don't think there's any point in Europe where 4 countries meet at a point. All right, well, task for the student. Anyway, so the restriction to trivalent graphs means that my results apply for Europe. Anyway, so that's that there. And so the map now is, we basically take every line segment of the original one, and I replace it with 2 lines in, let's use different color. 2 lines in temporally lead, but not quite. So not just, sorry, I guess I could have thrown it vertically. So anytime I have a graph, I take every line segment in the graph and I replace it with 2 lines in temporally lead. That's why it's n and then 2n here, but with the following linear combination. So it's not just plain 2 lines. I draw it like that, but what that means is it's equal to just have 2 lines non-intersecting minus parameter 1 over d. And now relate the parameters now. The parameter in the chromatic polynomial is q equals d squared. And then what it says now, so I do this over here, so literally I just take the same graph. Oh, sorry, I have to tell you one more thing, but what to do with the vertices. So let me first do the line segments, and then I'll tell you how to deal with the vertices. That was like that. I'm going to do this. Sorry. Prematurely drew the picture. So now then when I have a vertex in the original picture, I replace it now those lines, notice they don't intersect, and then I put this projector on there. And then for convenience sake, I multiply by this factor d to the 1/2. Okay, and so now since we have 1, 2, 3, 4 vertices, this would give me a factor d squared there when I do this replacement. And so now the result, which is an old one, in fact, it goes back to more or less the same year where Temperley Lieb did their work on this. So this was long before Jones. Jones independently rediscovered some of these things. More things too. And so what then we say with this map, what we have the result then is if you identify q is equal to d squared, what we have is this normalized chromatic polynomial that down, and sorry, is then the evaluation of phi this graph. And by the evaluation, I meant what I just said a few minutes ago. Evaluation just means d to the number of loops. So that's the result. And this is a rephrasing of an old result that I think was first in statistical mechanics or maybe in combinatorics. It came from what's called, in physics language, the Fortune-Castellan cluster expansion of the Potts models. And in one of these amazing cosmic coincidences, Tutte invented this object called the Tutte polynomial for various reasons. And well, among them, it was the most general object he could find that satisfied contraction deletion. And so when you, so when you specialize that polynomial to particular values and use this particular kind of cluster expansion, you get this result that I just said. So since I don't have a ton of time, I'm going to skip the proof of that result, but it's not hard at all, and it's old. Okay. Questions on where that? So that's the result we're going to, well, that's crucial to what we're doing. So the reason we do this, so why phi, why this map, is because within temporally and the fusion categories in general, there's special objects called Jones-Wenzel projectors. And what I'll explain is that special values of D, the trace of these projectors vanishes. And then that starts to smell like what I told you at the very beginning, the linear identity that Tutte did. And so in particular, well, let me write this down. So for example, yeah. In fact, already I've written down an example of a projector. So this is what would be Jones language. This would be the projector onto, well, if you like the physics nomenclature, spin 1. And so, you can do this graphically given the temporally Lieb relations do this algebraically given the temporally Lieb relations, but let's check now that this is a projection operator or an idempotent, sorry, I should have said in mathematical language. If I take P1 squared, I get P1. And so let me show you how that goes. Anyway, so if I just do this twice. Well, all it says is when you have that, you plug that in, so there's 4 terms there. So I get that one where I go straight through. I'll get minus 1 over d this, that. And then I'll get plus 1 over d squared times that. Well, those can't do anything with, but this one we have our rule that we can remove the loop by multiplying by d, so that goes 1 over d. Doesn't quite cancel this, but then this is equal to this minus 1 over d times that. I'm allowed to move everything around. So that's the proof that P1 squared equals P1. But what Jones and Wenzel explained a long time ago is you can do this. There's one of these for one new one you get by increasing the number of strands by 1. I should have said I haven't mentioned quantum groups. Some people here like quantum group algebras. These are basically the analogs of projection onto irreducible representations of quantum group algebras at roots of unity for the quantum group parameter Q. Anyway, so you can get other ones. Let me just write down a general formula for them. where Pn, you just build, this is just a recursion relation that builds them up. So this would be Pn minus 1, and I put another strand here. So this would be some projector onto n strands. Draw it like this. And we get Pn minus 2. And, sorry, there's a constant there. And where? Delta n is the trace of p to the n, defined in the same way I did it with chromatic algebra. You just run everything around and then evaluate it. Here there's only loops, and it's easy to compute that this trace is equal to, where's the formula? To emphasize the connection with quantum groups. Again, for those who notice, this is the same Q that appears there, where D equals Q. All right, so now we're almost there, actually. It's, so these special things exist. But the key observation when Q is a root of unity, so when D equals 2 cosine, so special case, sorry, let's leave that there and let me go back there. So again, so that one, proof, but proof is old and easy. Well, it wasn't obvious, it's not obvious. Figure it out, it's easy to prove. That one I just erased, so this one's pretty easy too. So the point is when Q, this little q is equal to e to the I pi j over k plus 2, j and k integers, let's say positive integers just to avoid some complications, then in this delta n, which is the trace of p equals 0. This is quite obvious from this formula when n plus 1 is equal to k plus 2. So these are the cases, to go back to the language of D, I've been using this as D equals 2 cosine pi j over k plus 2. That's all. So then, this is an ideal. If ever this combination appears, you can set it to 0. Set Pn equals 0 inside the graph without changing the evaluation. Is a remarkable thing. That's why these things are topological. So these special properties, they're very. But now, I told you a few minutes ago that I could reduce the thing I just erased here. But chi in Q comes from evaluating this double graph, this temporally lead at D equals the square root of Q. Up to the square root of Q. By that map I showed you before. And so then the pullback, so you can now pull back these projectors of Jones-Wenzel projectors into chromatic algebra. And this gives you identity. Gives these identities, like I showed, gives linear identities. The chromatic polynomial. At those emphasis at those special values. And so, so that's the thing Tutte found 30 years ago, but now we have this there. We have this for all rational values of this fraction. And so that greatly generalizes this linear identity Tutte found by hand in the late 60s. Or no, sorry, that one? I forget where he found that one. It's in his book. I'm sure he found it long before it. Long before he wrote the book. His later book, he wrote a couple books. And so it works. And so that shows that one. One thing, again, if you know anything about the chromatic polynomial, these values, so q is d squared, and for j equals 1, these are called Baraha numbers. And long ago, I think purely by just checking cases by hand, Baraha showed that the complex zeros of the chromatic polynomial for q less than 4, so notice d is less than 2 by this, so q would have to be less than 4, they accumulate, numerically they seem to accumulate at these numbers. And that's still mysterious why that is. And now we've made another level of mysteriosity as to why it's at these values, precisely these added properties. Okay, good. Since I don't have a lot of time left, let me then, again, so the proof of these, the projectors is easy, and then the pullback is easy. So now let me just, since the talk had golden identity in the title, let me just say schematically how that goes. So what happens now, so if I take this golden identity that I wrote down at the beginning, let me rewrite the golden identity in terms of the dual graphs, the countries. So we have chi of g so this is the golden identity. Equal to, so that's the golden identity. Again, Tutte proved it, but we can now prove it much more straightforwardly. Well, at least once you know the things I just told you about. And so basically, all you do, so I'll just do this schematically now, because we really don't. So again, we have some graph here, we have some vertex there. And so literally, all I do is replace this now. Well, so this is some graph here, g hat. So we've got a graph g hat here, but this is squared. So it just says that we're going to have sort of two, if you're squaring the chromatic polynomial, you're taking two graphs at the same time. And so we define a map, again, just like we did to temporally leave. We take this map of this graph to this two graphs, and again, just for convenience, we put 5 to the 3 halves to take care of the number of vertices there. And then we can use a map phi cross phi to send this to temporally lead, cross temporally lead. Right. And then we use the linear Tutte identity to show that this thing satisfies all the three relations that Well, so the right-hand side, those three linear relations I wrote down towards the beginning of the talk. So they were, a single loop gives me q plus 1. The tadpoles vanish. Those two are obvious just by drawing the pictures. The one that's not obvious is the one that plus that equals that plus that. So that's true by definition on this side. It's not obviously true here for this square, but you can show it is by using that identity I just derived using the Swenzel. So that's it. I mean, it really is just drawing a few pictures and then we're done. So I'll spare you the pictures, but there's really nothing more if you want to see how to do it. Okay, I promised I would say something new. Everything I told you was in a couple papers, Slava Kryshkal, and I wrote, 2008, 2009. I've been, for a variety of reasons, that if you want to come talk to me, I've been thinking about this again. I just wanted to alert you to a neat result of Ian Agel and Slava Kryshkal. The papers I wrote with Slava were ones from 10 years ago, and that inspired Ian to get interested. Again, I mentioned, famous mathematicians, still everybody wants to prove the four-color theorem a different way. And so I think perhaps that was one of the motivating factors deep down. And so what they conjecture, so here's an interesting thing. So first of all, so I've been going back and forth between the original picture for the chromatic polynomial, which I called chi of t in that language, and then something I do for these dual graphs, the graphs of the country boundaries that I've been using for the whole talk. So that one is called the other one. So on the plane, the two are equal. So that's why everything I said before was totally fine, as long as you're on the plane. But not on the plane, it's easy to see these two are not always equal. They can be. So if you look at non-planar graphs, the one I get using, so this was using the boundaries of the countries. It's called the flow polynomial. Again, you can get it from the dual limit of the Tutte polynomial. If you know about duality in the Potts model, this is where that comes from. So this was for using the countries themselves. So those two aren't equal, not if for a non-planar graph. I mean, they're not generically equal. They may be equal, not generically. They're not the same. But here's the interesting thing. So then you can ask, does the golden identity apply for non-planar graphs? So you can define everything just, I said, using the chromatic polynomial. You can define it on abstract graphs. It's all good. And then you can see easily it's not satisfied in general. But sometimes what they showed in this paper, you can find graphs for which it is satisfied, non-planar graphs. Now the very curious thing is, so I said the flow aren't the same. So what they have now is something even funnier. I have a conjecture. So this is a conjecture, well, mainly based on just looking at lots of chromatic polynomials. So then you take this flow polynomial, so the one in the other picture, the one I've been talking about all the time, and so you, first of all, they argue the conjecture there's an inequality, and moreover, the equality is only if the graph is planar. So Tutte's golden identity, oddly enough, becomes a planarity detector, if this is true, which probably, I think it is. They've checked it for tens of thousands of graphs. Mathematica can generate these things, and there's tables of these things. So anyway, so it's a planarity detector. So you just evaluate, you find the chromatic polynomial of a graph. If it satisfies this equality, then it's planar if this conjecture is true. So anyway, so that's pretty neat, and it's pretty puzzling because it's not quite obvious. It's not, doesn't seem wrong, but on the other hand, it's not at all clear how to prove it. This inequality is very strange. That's all. That's the whole choice there. Okay, sorry for running a little over. Thanks for listening.
Is the conjecture still for triparallel graphs?
Oh yeah, sorry. Thank you. Yeah, for trying. Yeah. I'm sorry, I didn't say that. Yeah, triangle graphs. Yeah, it just plain doesn't. And I can't remember now if the inequality might hold for 9. Let's probably not. So this is all for G trivial. It's, yeah, I'm pretty sure. Which is very curious. In fact, there's very curious because in our original paper we had some sort of a hand-waving way of understanding this via this level rank duality again of these fusion categories, and that doesn't say anything about working only for trivalent graphs. So it's a little bit puzzling as to why that is there, but it's definitely there. You can check that there aren't any. I mean, there are counterexamples to it for non-trivalent graphs.
Yeah. At the beginning of your talk, we formulate for color theorem in terms of, and you said it is strictly positive for Q equal 4.
Yeah.
Should we expect it is also strictly positive for non-integer between 3 and 4?
Oh no, it definitely is not between 3 and 4. You can find graphs that have it. In fact, there's a nice, in fact, it hadn't been found until maybe 10 years ago. Graphs that had zeros all the way up to 4. So it actually wasn't proven, but then just order 10 years ago, Gordon Royal explicitly just constructed graphs which had real zeros arbitrarily close to 4, which was pretty weird. I mean, yeah, it was bizarre. But here's an interesting thing that's not been proved. So it's been proved that it has no zeros on the real line for 5 and greater, but it's never been proved between 4 and 5. So again, there's no counterexamples to that, so everybody believes it's true. But the brute force method that these guys did on the computer doesn't, they just plug in Q equals 4 everywhere and just crunch and just check. They didn't have the chromatic polynomial. They just checked the colorings by hand by some. I'm not sure how they did it. So that's an open question. So between 3 and 4, absolutely, I think it's not clear whether it does. In fact, you can use this. You can prove, for example, I think at no Baraha numbers. So these funny numbers I said were Q equals 2 cosine pi over k plus 2 squared. I think, I won't 100% swear to this, but I think you can prove for all these values it's always non-vanishing. And there's other values for which it does vanish. So in fact, yeah, this is Mike Friedman or the wisecrack. This is sort of a 5 plus the square root of 5 over 2 color theorem, because this that you can prove isn't zero. In fact, I think I have to take back what I just said. I don't think that's proven, but you can prove that at this value there's no zeros. Although it's very small for what there's a bound on it. And so then this one, of course, it has to be. Actually, that's right, because this one you can find negative values of this. But on the other hand, squared, of course, gets positive. So this proves a 5 plus the square root of 5 over 2 color theorem. But that's just one point. It's a curious business, and that's why I think so many people, including me, get a little obsessed with it. Because there's clearly some structure there that nobody fully understands.
Any other questions or comments? Unless, thank the speaker again.
Thank you.